Okay, so we continue with our journey through identification this morning. So Paul explained very well deterministic identification, but also a little bit of randomized identification from a theoretical viewpoint, from this information theoretic analysis. But of course, at the end, you want to use them and to implement identification codes. And I think Caspar will now tell us somehow how to implement this. And yeah, Caspar is from the Deutsche Telekom chair at the TU Dresden. He's doing his PhD with Frank Fitzek, and he's working in the 6G Live project and in ComNet. And there we try to implement identification codes. And yes, I think we make big steps during this project, and Caspar will tell you now some results. So the stage is yours.
Yeah, thank you, Christian. Yeah, exactly. So I will be talking about how we can move towards more practical identification codes today. So the idea about making using identification codes is, of course, to become more efficient in the identification problem. And the idea that we have at the TU Dresden side of 6G Live is to make it a little bit more practical, right? Because the promises of the information theory side are really nice, right? And today Paul also talked nicely and also very entertainingly about how we can shift the boundaries of what is maybe achievable with different kinds of identification codes. But there is still some gap, we think, between this theoretical potential that has been shown and proven right and what we can actually do with identification codes at the moment. So this is what we try to do to validate these theoretical findings by just implementing them, looking at use cases, and then taking a step back and looking at what are the problems. And one thing that we found when we were implementing these was that the measures that we use in the proofs, right, some of them Paul talked about today, are not always the only things that help us to evaluate what constitutes a good identification code, and that they do not always help us in deciding what is a good code in a practical environment. So one of the questions that we asked ourselves was, can we find other metrics, new metrics that complement these in other ways so that we can really evaluate them in practical settings? Later today, I think Usman will also talk about the implementation from a software side. I will just focus on the implementation in terms of how to construct such a code explicitly. So it's still theoretical somehow, but it's not about achievability, but it's about mathematical implementation, basically. So for the identification here, I will just briefly go over again what Paul already explained so nicely, because this is again about randomized identification. So in our model, we have a sender and a receiver, and they have each a message A for Alice or Leia, or what's her name? I don't know. And Bob has message B. And then we have an encoder on the sender side and what we call a verifier on the receiver side, because the receiver just does this yes/no answer. And yeah, I prefer to call it a verifier because this emphasizes that this is not like a proper decoding with lots of work, but it's a very simple yes/no test. And then what we will focus on here is this ID encoder that maps this large message to a short identification code word. Behind this noiseless identification encoder, we have a channel, of course, but in randomized identification, there is this method of separating the two. So we have in the first step the encoding that is specific to the ID problem. It's for the efficiency, basically, and still offers reliable identification. And then to overcome the channel that does some distortion and changes some symbols, right? So here the 0 is changed to a 49, for example. This can be done by a conventional channel code. And I will not talk about this. So all that I will talk about is what we call noiseless randomized ID codes. So we have an identity channel, and the code word C that the sender selects is always correctly copied to the receiver, basically. And then the issue is about how can we shrink this message as much as possible to a short code word C, and then recover at the receiver side whether these two messages are the same or not. In this scenario, so generally, when we identify, we have 4 possible results. So we try to find out whether these two messages are the same or not, right? So either we have equality between the two messages or inequality, and we try to discern this. And then here we have either the receiver says, yes, they are the same, or no, they are not the same. And then, of course, this can either be the correct answer or the false answer. And in noiseless identification, we can never have false negative results, at least with the codes that we use. And so the only thing that can happen is a false positive. And this is, of course, because we we reduce this message to a smaller code word. And of course, there will be some clashes, there are some collisions, as we already saw in one of Paul's slides, where these sets overlap, right? And then different messages can share the same code word. It's kind of the pigeonhole principle, right? Because there's just not enough code words to fit all the messages. But because there's no error in the transmission, there are never any false negatives. So all errors that we will talk about are false positives, where the receiver thinks that the two messages are actually different and the receiver thinks they are identical. Okay, so how can we do this then in practice? I use circles instead of squares, but apart from that, it's very similar to what Paul talked about. So again, we have a message A that is encoded to a code word C, and this code word C is the dark dot within this larger set, which is the light blue circle that is associated with the message of the sender. And then because we have an identity channel, there's no distortion or anything. So the receiver basically operates on the same sets. So we have the encoding set and the verification set are just the same set, and we only test on the receiver side, is the code word that I received part of the set that I'm interested in. So for example, here the receiver is interested in message 3, so in the yellow set, and the sender unfortunately selected a code word that is part of C3, and therefore the result will be a match, even though message 2 and message 3 are, of course, different. Now, what we want to do is to talk about the error probabilities, because in the end, what we care about is how reliable can this be, right? We can become as efficient as we want, but if the error goes to 1, it doesn't matter at all. So what we really want to do is to quantify how often do we make errors. And to quantify it, it's all about how large is this overlap between these subsets of code words. Just to go back a step, of course, I call them subsets. Paul usually called them probability distributions. It's just 2 words for the same thing, because in the end, we have a uniform distribution over all code words that are part of this subset, at least in the coding methods that we use at the moment. And therefore, any code word that is part of this larger blue set can be selected uniformly at random. And therefore, to characterize the error probability at the receiver, we have to look at the code word set of message A and the code word set of message B, and then we look at how large is the overlap between the two, and how large is it in relation to the size of all the code words of message B, right? So the larger the overlap, the more code words the sender could select that the receiver will then take as a positive result. And typically then for the proofs, this probability is then characterized with an upper bound, because of course each pair of messages has a different overlap between their respective code word sets. And because there are so many of these error probabilities that depend on each message pair, and they are distinct to each pair of messages, we just find a bound and we know this is the worst case, or this is the highest error probability that any pair of messages can exhibit, and we find a bound. And then, as Paul already talked about, if this bound goes to 0 in the infinite regime of code word lengths, then we know that all the others are also approaching 0. Anyway, I hope you can, I'll just talk about it in a different way. So for the notation, we have So the error probability P for messages A and B, and it's, as I said, just to emphasize it again, it's not global, but each message pair has a different error probability. So it's kind of complicated in that regard. Then we have this bound that we talked about already. Then we have the distance between these two. So the distance is important because it's basically just the inverse of the overlap, right? So here I characterize the overlap between CA and CB, and the distance is just the inverse of that. So it would be C3 minus the overlap between the two, right? This will be important later because we will want to talk about the distance between code words and so on, and talk about maximum distance separable codes. And apart from that, yeah, we have the sizes of the messages, but I'll just skip it because it's not really readable here. Okay, so as I just introduced, the distance between these code word sets is what we really want to focus on, because if we have a high distance between these subsets, so if these circles overlap as little as possible, we have as few errors, or sorry, the error probability is as small as possible. And currently, the only method to construct noiseless ID codes are so-called tagging codes, and they repurpose error correction codes. So linear block codes that often have known distance properties, and if they have a high distance, we can repurpose these error correction code words as tagging code word sets. And yeah, this works as follows. So we have a message A again, and it maybe looks like this. So we have K symbols in base Q. And then, because we want to increase the distance between the code word sets, we have to create this code word set of the message A. And we do this using, for example, a Reed-Solomon code. So we increase the number of symbols from K to M. And then we treat this not as a Reed-Solomon code word, but we treat it as a set of code words. So each symbol in this Reed-Solomon code word is one of the tags. So each symbol is a tag, and this is why it's called a tagging code. And then we also associate with each position the number of it. And this position 2 with the tag value 14, for example, is then the dark blue dot from the previous slide within the larger set, which is all of these M tag position pairs that constitute this subset of code words. And yeah, and we select one of these positions at random and call it the noiseless ID code word C. And just as a side note, maybe for the size of this code word, we now have like this small m. So this was these two symbols that we saw before. So this is much shorter than the k on the top, right? Because we want to be more efficient. So if m is larger than k, we didn't gain anything, and we might just use just transmit the message instead. And another thing I want to point out is that the random position, we call it pi here, it's much larger than the symbol size. So the subsets are pretty large, and the tag itself is pretty small. And we select this position randomly, right? So if we can somehow get this random position more efficiently, for example, if we have some kind of common randomness generation, or even simpler, if we just have a random number generator, we only have to transmit the tag, and it's even more efficient. So this is kind of an important aspect, but this is just a side note to relate maybe to the common randomness talks that we heard yesterday that can benefit the efficiency of randomized identification. Now on the receiver side, we basically do the same thing. We have a message, we create this set of code words, and now the sender sends the ID code word to the receiver, and then the receiver checks at my position 2, what is my tag value in my set of tags? And then if the 14 equals the tag value of the receiver, then you know it's the same, and otherwise you say it's different. In this case, they are different, the tags are different, and also the messages are different, and therefore the receiver can conclude that these messages are different, which is what we want to have, right? So overall, then it can look like this. However, now to come back to the distance properties that I talked about before, Of course, because we have this overlap between the different code word sets, there will also be times where we select a tag that is the same as another message, right? And we want to minimize this. So in this example, we again have these two code word subsets, right? And this position 2 that the sender selected. And this is fine, right? But if the sender would have selected position 1, we would have a clash because both have position 11. And now the property of, for example, Reed-Solomon codes, but also other high distance codes comes in helpful or handy because we have a high distance code, and because the code is high distance and this set of tags, or at least, right, the set of tags has a high distance from the set of tags of all the other messages because it's guaranteed by the construction of the code that guarantees that in most of these tag values we differ from all the other values. Therefore, if we have a high distance between these block code words, we have a low collision probability and we can bound it, right? So we know the maximum distance of a Reed-Solomon code, and therefore we know the error probability that a tagging code can have based on Reed-Solomon codes. Is that clear? Okay. So how do we evaluate this? We want to talk about the collision probabilities, right? So now we have a tagging code. We know the maximum distance of a Reed-Solomon code. The maximum distance is the inverse of the overlap. And with the overlap, or the distance and the size of each code word set, we can just divide one by the other. And then we know, I don't know, there are 10 positions in which we can make an error and 100 positions we can choose from. So 10% error probability, for example. And this is for the worst case. And we know for all the other ones, they have an even higher distance. So they have an even lower error probability. And then we are even better off. Maybe I go back a step. The issue is, now when we want to evaluate it is that the error probabilities are of course characterized nicely by this upper bound, but there's more to it, right? Because it's not only this worst case, but there are also lots of other pairs of messages. It's not only the worst case error probability, but we are also interested in other error probabilities. Because, for example, if the receiver selects message 5 and the sender selects message 2, the error will be much nicer. And therefore, we introduce no code as a baseline. So what we do there is that we do not use the encoded tuple of tags, which would be where the M sits, right? But we just take the message itself and we sample tags from the message itself. Of course, this is not a good ID code because we don't have this high distance property anymore, right? Because we did the encoding to introduce high distance, to reduce the errors, and so on and so forth. However, with this no code, at least we have some kind of baseline to work with, right? This is what we get for free. We don't have any coding complexity. All we do is select a random symbol from our message. And this is helpful because for Reed-Solomon codes, we do not know the distribution of distances between code words. There are some bounds, but there's no closed form solution for it. But for uncoded noiseless identification, it's a simple combinatorial problem, and we can just show it. And then what we did was to do some simulations to just we just evaluated it basically in an experiment what the distribution of these Reed-Solomon distances looks like. And for the no code, for the uncoded identification, such a histogram can look like this. So we have a few message pairs that have a low distance, right? And then it rises and then it falls down again, right? So we can characterize the number of pairs of messages that have a high overlap and others have a low overlap. And this is interesting because So for the proofs, we really care about showing that in the infinite regime, everything goes to 0, right? We have a bound, we shift the bound to 0, and this whole histogram just gets squished towards 0. But in practice, we are not in the infinite regime, right? In practice, we have maybe 50 bits or 100-bit code words, and the error does not go to 0. Maybe you have 1% error probability or 10 to the minus 6, but it is finite, and there are important trade-offs between, do we increase the size of the code word, do we decrease the error probability, and therefore the bound can be helpful, of course, to characterize it, but the whole distribution is really important to us. And what we found is that it looks something like this. So this just schematically, of course. So again, we have in red, we have the distribution of pairs for a good ID code that can approach 0 error probability in the infinite regime. And it's subject to this lambda 2 bound that Paul also talked about, right? So all of the message pairs have an error probability that is lower than this lambda 2. So yeah. And for the blue line, this is this uncoded identification. There are lots of message pairs that have higher error probabilities because the bound is basically 1. So there are message pairs that are the same in all but one symbol. So of course, there will be a very high error probability between these two. However, this tail of high error probabilities, it's very small because of this combinatorial problem. The probability, like given that each message is selected equally likely, it vanishes really fast, right? So even for very small identification codes, the probability, if every message is selected equally likely, the probability to select two messages that produce a high error probability, it's very low, right? So what we really care about now is what does the use case look like? What kind of messages do we select? Do we really need these kind of guarantees, or can we get away with no coding at all? I want to point out again the proofs and the information theory here is of course interested in the worst case, because if you can manage to guarantee things for the worst case, you can guarantee it for everything, right? So what we say here is not that these bounds do not help at all, but it's about, we have the bounds now, but can we not broaden the perspective a bit and look also at other aspects? Because the intuition here is maybe that identification codes also introduce so to go from transmission codes to identification codes, we also introduce on purpose more like an additional error probability, right? Because we allow for this overlap of message of code word sets, and we loosen this, and then we show again, and this probability now goes to 0. And this is, like, from my perspective, a similar philosophy. We loosen this need for a tight bound on the error probabilities, and we say, look, this part of the tail is so small that it maybe even vanishes, depending on the use case. And bear with me on this one for now. So just look at the blue line maybe. So this is again a histogram. So here we have again the error probability. And here we have now not a count of message pairs, but just a probability of selecting it. And in blue, we have a uniform distribution. So we just have basically a Gaussian curve, right? Or a binomial distribution because it's discrete. And the continuous line in blue here is what we get for a Reed-Solomon code, which is the good code, right? Which has nice properties. And the dotted line is what we get for free. And then we show here what happens if the distribution of messages is not uniform anymore, but it becomes skewed. So some of the messages, or we do not select anymore messages that are good, but we typically select more and more messages that have a bad overlap behavior, right? So they have a small distance from each other, and they collide with each other, right? And therefore, this is what I showed earlier, and this is why we need the bound. This distribution moves more and more to the side, and it becomes more and more skewed towards higher error probabilities, because in these use cases, we have we are unlucky about the messages that we select, and therefore the error probabilities get higher. And this is important because the mean error probability, if we take, I don't know, 1 million runs of this identification process, this mean rises, of course, because the messages that we select have a bad behavior, and therefore the mean error probability rises. And we think that the mean error probability is in the end very important as a practical metric, because if you run an identification system for a year, you want to know how many errors did I make. Was it a problem or not? You don't want to have the bound. You want to know what is my expected number of errors that I make. And the relation between this expected number of errors that we make and the error probability bound is that the bound gives us the worst case, right? So if we select the worst messages and we run this worst message pair for the whole year, how many errors will we make? So to make this a bit easier, maybe, this is kind of a meta plot about the previous one. So if we this one, if we increase the skewness, basically, so if we increase or if we decrease the number of messages that we select, where does our error probability go? And we show here first the worst case, which is the orange line, and you see that it rises in the worst case, as we saw on the previous slides, because of course we select worse and worse messages, and we did not find this in the experiments, but generally this is of course expected to converge on the upper bound of these Reed-Solomon codes for the fixed line. For the uncoded identification, you see it's unbound, so it goes up quite a lot, right? Because we have the worst case, we don't have any bound, the error can go to infinity. However, if we happen to select the best case, it also goes down a lot because the distance is small, so we only have a very good message pairs between them, which have a high distance from each other, even though we don't guarantee this. So really what is important is, what kind of messages do we select? And do we always need to provide this bound, or can we make it a bit lighter? For example, here we show we call it row 2, which is a quantile error probability. So it just guarantees 99% of the message pairs have an error probability lower than this value. And we can see that it is slightly above the average error probability, of course. It's not the bound, but it's a quantile, right? And we can see that it is, if you look here, so the straight line is the Reed-Solomon code, and then the dotted line is the uncoded identification. And we can see that this quantile error probability is higher for the Reed-Solomon code, that is supposedly better than for the uncoded identification. And that is because, if we go back here, because if we select some of the worst pairs, but not all of them, the mean, so we cut off some of the messages that have very low error probabilities, but we keep all of them on the right side. And because the red curve here is skewed to the right, we experience that the mean error probability rises faster because the tail of the blue curve hits in much later than the fat tail that is bounded of the Reed-Solomon code. Yeah, so what we found here is that it might be a good idea to soften the reliability guarantees of identification codes and to think about quantile error probabilities, because these are, of course, softer than the bound, but they are still stricter than just the mean error probability. So we kind of can broaden our perspective on identification codes. These quantile error probability bounds can be cheaper to achieve than having these strict lambda2 bounds. And they also point that we should consider the properties of the source a little bit more. I know that Olaf is working on source identification as well, and because noiseless identification does not have to consider properties of the channel, it's kind of natural to think about, if you think about this source channel separation, that noiseless identification sits kind of between channel coding and source coding a little bit. And I think that noiseless identification codes can benefit from incorporating some aspects of the sources and what kind of messages they produce for us. And therefore, finding also better bounds maybe about the distance distribution of other linear block codes can be helpful, because the shape of these distance distributions matters a lot for the quantile error probabilities. Yeah. Thank you.
Okay. Yes, thank you for that insight. So there's a question.
Thank you for the presentation. I have a question about how you use Reed-Solomon codes and you compare the results you obtain with the Solomon codes with uncoded identification. So with Reed-Solomon, you have some, Reed-Solomon is defined on a certain finite field. And when you consider uncoded identification, what is the alphabet for the messages? And if there is an alphabet that is the same as I assume as the Reed-Solomon code, how would these results change with the size of the alphabet?
Yes.
Thank you.
So what we do is that we always consider the same alphabet size, because the average error probability is 1 over the symbol size, right? It's just, if you have 8 bits, it's 1 over 256, for example. So changing the alphabet size would, in our opinion, be an unfair comparison, because it's also, and the tag size also is 1 symbol, right? So if you send 8 bits, you need to stick with 8 bits, because otherwise the comparison becomes unfair. And then in the second step, there are 2 things that you can equal to make the same. Either you support the same number of messages as a Reed-Solomon code. If you do that, then your code word becomes much smaller, because the scaling, right? Yeah. Or you say you have the same code word size, and then you support many more messages. And so we just compared both. So here we have a Reed-Solomon code with symbol size 13, and then the inner dimension, because it's a concatenated Reed-Solomon code. It's the Verdu-Way construction from '93. So we have an inner Reed-Solomon code size, or dimension, sorry, of 2, and an outer Reed-Solomon code size of 13. And then we can use either an uncoded identification scheme where the message size has 26 symbols, and then we match the number of messages, or we have a uncoded identification scheme with 2000 symbols, and then we match the size of the sorry, I got it the wrong way around. So for 2000 symbols in the uncoded, we have the number of messages that the Reed-Solomon code can support. And for 26, we have the same code word size. And yeah, so I think you always need to compare both, because it's not clear if you want to have the same efficiency in terms of how much you send via the channel, or if you want to support the same number of messages on the for the use case. Yeah. Exactly.
Okay, then Casper again.